Okay, hi. So we continue solo neetcode task, and we continue with trees. So I will call this 14 days trees challenge, and we are going to tasks, and we have the medium one that costs lower common ancestor of binary search tree. So let's go and check. Right. So let's decline it. And let's check what we need. So we are given a BST, so it's binary search tree. We have to find the lowest common ancestor node of two given nodes in the BST. According to definition, so the lowest common ancestor is defined between two nodes, P and Q, as the lowest node in T that has both P and Q as descendants, where we allow a node to be descendant of itself, where we allowed to be descendant of itself. So for example, we have node 2 and 8 here, and we see that the lowest common ancestor would be 6 here. So we return actually the value, the tree node with 6. Then here we have 2 and 4, and we see that they are on the same path. So we return 2 because like 2 is the common ancestor. So what we should do, so as we have by BST, we actually can create a set of nodes. So it would be kind of a path for ourselves, and then what we can do, we can so when we have a path, we can create another path from another node. So we have two passes, and after this we can just go one by one from the end, from each of these nodes, and then just return these values. So what we need to do first, I think we need to create a set. So first it would be like a set of 3 nodes. So it would be a path, so get path from root, let's say P. Then when we have a path, and after we have this path, we can create another path. Yeah, but in this case we should have like a list of 3 nodes. It would be path 2, like gen path, it would be the second function from root to Q, and then we just iterate from path 2. So it would be 3 node here, path 2, and if path contains n, we just return this n. Otherwise, we return null. So let's create these two functions. So first function, it should return a set for us. So we have set 3 node. It's called get path. We have two functions. First through root and p, and and in this case, so when a root is equal to p, we actually start returning I think here we can like new hash set, and here it would be a set of our 3 nodes. That so when root is equal to p, we return the set, and also we put, of course, to we at the beginning we add to the set value of root. Yeah, and then here we check if root value is greater than p-value, then we go one way, otherwise we go another way. So for example, root value is greater than p. So for example, we own 6 and we are we have 2, yeah. So we are looking for 2 and we see that root value is greater than 2. So that means that we are going to the left. So we call get path from root left. Here it would be p and here it would be set. And here we go like other way wise to do the right. So we have one function and then we need another function with list. So here it will be turn node, genpass, and in genpass we have also root and pq. So in this case, if root is equal to p, we need to yeah, we need to create a list, new array list. List of 3 nodes. Here it will be results, and here we add to our result root, and we actually return a result from here, and then we do have the same value, the same path here, and yeah, from each of this node we return this result. And we return result and return result, and in result we add root, here we add root. Right, so we have genpass and then getPass, and then we have this for loop. So let's run. All right, so we have completion error. Let's check. Yeah, so we have this set, and we don't have this set here, so we just remove. Let's run. All right, so it's not cat, but in genpass. And here I think that we return set, so we should just return from here. Okay, so we accept and submit. And we also accept and submit our completion. So let's check with previous implementations. So previous is the same, like we have set, right? Then we have DFC. Here we have system out. I don't know why. And then found. Okay, so we have set. Then in DFS, we actually populate this set with values. And then we have this find operation. And in find, we actually find this result node. It's actually it's quite, I think, more productive than, but the core logic is the same. Here's also the core logic the same. Let's find some implementations in Java. So we have even more, even better implementation, but I think this one, it's more clear. So we're done with today's task, and tomorrow it will be inserted into binary search tree. Thank you. See you tomorrow.